We are a small nonprofit located in the Los Angeles area. My team and I used to be at UCLA. We left in 2010 because we wanted to write a curriculum for middle school students. We have accomplished that goal. We now have a 6-7-8 program, and we left UCLA and are living happily ever after. So I just wanted to give that as a way of introduction. Today, I'm pretty excited, a little bit nervous about this talk, which I have not done before. Could be a big hit, and if it is, I encourage all of you to do a great evaluation. Y'all know that evaluation thing? Okay, well, this is code 1 to elucidate. If it's not a great hit, I would appreciate the feedback. Good name, productive feedback. Thank you very much for the way. Okay. So I was inspired to, I don't know if you folks know that generally when those of us who speak are invited or apply in April, maybe. And so usually around April, I start thinking about what am I really into right now. That's what I was thinking about next year. And at the time, I was really into geometry because we were writing geometry. And I saw a couple of videos that inspired this talk. Those videos are actually referenced in your packet on the second to the last page. At the bottom. And it would be really cool if I showed you those videos, yeah? Yeah. Except this room doesn't have internet. So you're going to get one better than that. You're going to get me doing the video. And you're going to But the things that some of the things we're going to do today are, I hope you can see that I like to be interactive, engaging. We have materials to play or to watch. Some of the things we're going to do are demonstrations, and I'll let you know they are on the videos. What inspired me about these videos is that there was basically no language in them. They were all visual proofs or demonstrations, which to me is beautiful because it allows us to create a rich language environment in our classroom, especially for English learners, without having the interference of language. That might sound like an oxymoron, but if we can give students access to a concept and then have them talk about it, and then build language from that, they're going to make a lot more sense of it, and they will have a low filter of anxiety. So even though I talk too much, in this session, there will be times I hope when I shut up and just let the proof speak for itself. Okay? So, for example, on the front of your packet, I know all of you did these while you were waiting, didn't you? So at your table, and I'm not going to be giving you anywhere near enough time because we have way too much to do, but at your table, I'd like you to choose one or the other. Turn to your elbow partner.
I'm sorry, Shelley, if you've just come in, there's extra copies towards the front, and there's some extra seats, so we're inviting you to come forward. So there's plenty of handouts in the front rows. If you're coming late, and I'll let. Sorry.
Okay, so at your tables, would you find yourself a nice partner for a session or 2 or 3? Take a look at these little pictures. What is a trapezoid? What's a triangle? My language prompts are pretty simple. A equals. What is the area? And how do you know? Or why? Pretty simple prompts. A equals Y. Take a moment and talk about those two, please.
Even looks like it's a matter that it's not.
I don't know. That's why it's two.
Yeah.
Okay, now it's time to bring it back to the floor. Is there anyone who would like to describe to me how you found the area of the trapezoid? The area of the trapezoid. Anyone who would like to describe it to me? Or the triangle? You all are going to be silent partners in this talk, okay? Go ahead, thank you.
I made the rectangle in the center, and I did the formula where half the base times height was the average of the two bases, and then times the height. But I just made the rectangle and then took the measure of each triangle, and that helps sum it up.
Did everyone hear what she said? Okay, I'm not going to write it all, but she made the rectangle. How many of you did something like this? And then she created the two triangles. How many of you created these triangles? Okay. She said that she used the area in the formula of a triangle that she knew to find these. How many of you used area formulas to work this one out? How many of you did some sort of accounting thing, accounting of squares? Okay. Do you see the variation even just with this simple little problem? Okay. I saw this on someone's paper. What else is? What's the area of this little triangle here? Mm-hmm. What about this triangle here? Half of 2 is 1, something like that. Okay. Being able to chunk a shape is a 6th grade standard for sure. Okay. How about this one? You want to go down a shot? Not quite as easy. Sure, sir.
Create a square.
Pardon?
Create a square and then subtract the area of the two triangles.
Say that
So
again.
you're going to create a square that's 2 by 2.
Create a square, did you say?
And it's 2 by 2.
Create a 2 by 2 square. Okay. Okay.
So we know that one line is going to be top. That's one, and the other one is going to be 2. But the area of the triangle you're looking for is something going on.
Y'all see what he did there? Okay. How many people thought about it this way? Only 2. Okay. What's another way? And so you found the area of these and subtracted from 4. Is that what you did? Okay. Yes, sir.
What I did is just the formula is 1/2 base is height. So the base is 1, and the height is 2.
Base
So
is
2
height.
times 1 is 2, and then 1 height is 1.
Okay. Knowing the formula? Yes.
I saw it as moving it, and then that way we would be like a rectangle. But it's basically the same thing as base times height. But I saw it as moving it for the first time.
So you saw.
I moved the bottom corner and we left it down to that.
You saw that those would have the same area. Okay. So this is just preliminary. We're looking at dot paper pictures. There's a lot of accessibility for students. In the classroom, as we would be discussing this, I would be creating some sort of a word wall or some vocabulary list where we are generating this vocabulary, and yet it wasn't here at all. So all students have access, especially language learners, will have access to this. Students who are not very fluent in formulas can count low floor to this activity, but as you can see, it's a pretty high ceiling as well. We're going to move on. So, by the way, on your table are some info cards. They're little cards that I would invite you to fill out if you would like. If you fill out that info card, or if you scan the QR code and fill out the information online, I will be happy to send you a copy of this handout, and I will also send you some other stuff. Okay, it's, but right now you're going to get a set statement, right? So and some of the things that I'm going to that are included are things that I couldn't put in the handout, but I'm going to show you right now. So if you're interested, fill it out, or give it to our children, I'll get that to you. So we're going to mainly focus on a lot of different shapes. As for polygons, we're going to focus on trapezoid, but I wanted to just show you a little bit of a quick progression of how we might get to trapezoid. So rectangles I'm not going to do, but what is this? Work on your visualization. Okay. How many of you have generated possibility for area formulas in middle school by having students kind of rectangles or parallels? We're going to do a little bit of that. And how many of you have not? Everybody does that? Oh, well, let's go to that. Okay, so one of the things that I wanted to share with you is that if you don't want to always be passing out scissors or doing pedals and everything, I would invite you to maybe show a picture like this and just say to the students, what do you see? What does this tell you? And these pictures tell a pretty powerful story. This is just the beginning one. I'm going to show you the whole series real quickly that you are welcome to with every while. But here's one where the students would be counting, perhaps, to figure out the area of the parallelogram, perhaps recognizing that they can turn it into a rectangle with a little bit of dissection. But what would happen if I gave them this? It's the same picture without the dots. We can now take our numbers and generalize, yes? What do you see? Really simple language, really rich conversation. Okay. Show you a few more. What do you see? See what I mean? Okay. After we've done that one, we imagine a cut and paste. What do you see? Here's another one. Which brings us to the trapezoid. Back to our friend trapezoid again. Okay, you ready? So we're going to do the trapezoid a little bit different. You may want to take some notes in your packet if you like. But there are trapezoids on your table. It would be nice for the students to actually use the manipulative and manipulate them around. And you're welcome to do that. But I'm going to do what do you see with you because it's the way. So. Can you pull it down behind it? Please. Thank you. talk about that on that table, please? What is the area and how do you know? Based on particular Is the area 18 units? Okay. And how do you know the area is 18 units?
Because if I take right
Okay, so I did not give you very much instruction, and this wonderful lady said, is the area 18 units? How many of you got 18 units? Anybody get anything different?
division.
What? What'd you get? 10 what? 10 what? 10 units squared. Anybody get anything else? Yes. 15 units squared. How many? 15 units squared. Anybody get anything else? This is unexpected. I love this. Okay, would y'all now at your table, please talk at your table and see if you can find some consensus of whether any one of these answers is correct or whether there's something else that is correct. Now it gets Oh, someone's asking, am I asking for the entire shape? Or just the blue shaded shape? Or the white shade, or the white shade? I like what makes it we have a longer time about. Okay. All right, so let's, all right. So I gave you some information. I asked you a question. I asked you to think about it. It's pretty open. We came up with all kinds of answers, whether you can justify or not. And then we come up with another question. What are we actually talking about? Okay, so let me give you some more information and let you go back to where I would like you to find the area of the original unshaded trapezoid. Talk about it at your table. Do we have the answer up there? Is there another possibility? What's going on?
evenly.
Okay. That's what brings us back anyone have some more thoughts about what the area of this trapezoid? Do we think the area is 18? Every kind of rules out with that, and we would have some conversation. How about 10?
Yes.
Huh? Half of 10. Yeah, half of 10. So the 10 answer was 10 square units, was the actual area of the full parallelogram, right? And half of that would be 5. Now, from this, we could, and I'm not going to right now, but we could put some numbers on there. The two lengths of the bases are 1 and 4. The height is 2. And so when we made that parallelogram, we see that the base becomes the 4 plus 1. Right? So this is giving us some insight into where the area of the trapezoid is right. It was not my intent to trick or fool you. It was my actually trick and fool me. I had no idea I was going to get all these answers, which was very cool, actually. It was my intent to strip away the language, to provide something open, and then let us explore. And through that exploration, we uncovered some really interesting things. I hope you saw that without very much language, we were able to get into this, that we needed clarification on what we actually found in the area, which was worthwhile. That if we started to write down the explanations, we would be getting some vocabulary, and we would also be getting a numerical explanation for this particular problem. Okay? We're going to go on to another trapezoid. I'm going to be a little bit more clear this time, I hope, and see if you can find the area of another trapezoid and explain to your partner how it works with a different diagram. So for there's a diagram that I'm not going to have you do right now, which is if we were to draw a line segment that bisects the trapezoid right in the middle, and we were to remove this piece and rotate it around, we would get right? If I take this up. You all see that? Cutting works really well then. Okay? Talk to your partner about what this means in terms of the area of parallelogram. In terms of the base, which are 1 and 4, and the height, which is 2. Okay. What does that tell you about the area of the trapezoid? Okay, I hope all of you found that the area of this trapezoid was 5 square units. Exactly what we did before. But I'm going to ask you a little bit of a different question now. Suppose instead of doing it on the dot paper, where we find it's 5 square units before, we did it without dot paper. I'm going to draw a line parallel to 2 bases that bisects this. I'm going to flip this around like that. Okay. I don't know how to part. Scissors. Okay. Now I don't have any numbers. I don't have any dots. But I play with parallel. Play with trapezoid. I play with parallelogram. What are the important and relevant dimensions that I'm going to need to know in order to describe the area of this trapezoid that I now rearranged into a parallelogram? What dimensions do I need to know? Yes?
Half of the total height.
Okay.
When you bisect it, what is the total height?
Okay, so I need to know the total height, right? Because I bisected it, which would give me half the height. What other dimension do I need to know? Huh? 2 bases, right? We all know this because that's why I read the math concepts, right? But here we go. So I had all these colored pencils, but they don't show up very well, so you can see it's markers. Okay, so down here, I'm gonna put my dimensions down below. This is gonna be in the textbooks you'll see it as B1 and B2. I prefer not to use subscripts in middle school whenever possible. I think there's enough abstraction that the students are learning that it's unnecessary. And so I'm going to call the bases A and B rather than B1 and B2. It just removes a little layer of abstraction. We need to know the height over here, which I'm going to put in here. Okay. And is there someone who can describe to me using A, B, and H how you would find the area of this trapezoid if I chopped it off in half, moved pieces around, and came up with this parallelogram? What would I have to do? What?
B plus A.
Huh? B plus A. Okay, so to begin with, my bases are up here, but by the time I get my manipulating, I've got B here, and I've got A here. So my base is B plus A. What is my height? 1/2. This right here is 1/2 height, which is going to lead me to the area is half the height times the sum of the bases. Okay. Nice. We're not going to do it, but I'm going to challenge you to think about what it would look like if instead of bisecting the figure by chopping the parallel, I just bisected the figure by creating 2 triangles. What was the base and the height of those? What would happen if I manipulated those? I'm not going to do it. I'm going to give you something. So going back to those little figures that I had from before, we can have an engaging open conversation where the students are playing and we're coming up with all sorts of shapes and trying to find the areas. Or if you want to just make it a simple what do you see problem, you could just put something like this up. What do these pictures tell you about the area of the trapezoid? What do the pictures tell you about the area? And once we've talked about that one, guess what the next one's going to look like? Either you want to trace again? What do these pictures tell you about the area of the trapezoid? What do these pictures tell you about the area of the trapezoid? What do these pictures tell you about the area of the trapezoid? So the formula, these formulas for geometric figures, I hope are not mysterious to students. I hope they don't feel that they're memorizing things that make no sense. But they're working with the figures and understanding how they can decompose them, put them apart, put them together again, double them, and create figures that they are familiar with, parallelograms, rectangles, etc., and see that these formulas are related and make sense in our life. And this kind of work begins with no language, but I hope you can see that you're going to have words with the conversation. Like the kind we had in this room. Not good. Okay, we're going to move on. Enough about polygons. Time to look at something else. How many of you have seen the area, the cut up through the area of a circle? Not too many. Okay. The cut up through for the area of a circle. How many of you have seen it? Okay. Well, let's do it. No need to look in your packet right now. I have here a circle. What does the black represent? What does the red represent? Pretty simple language. Okay. Can you see? I'm going to cut it into wedges. By the way, in this wedge, what does the black represent? On this one? Half the circumference. What does the red represent?
Radius.
What's the whole length? Vocabulary, without vocabulary. Got it? Okay. Moving on. We're going to make quarters. Okay. What is the radius of this one in length? What is it the same as? What color?
Red.
Red. I have to do a few more red. Okay, I'm going to do one more cut just to make it clear. These are supposed to be 8s. Okay. Now, let's take a look. I'm going to take these. Can you see? In the classroom, all the students would be doing this. In a room of 200, there was more that was cutting 200 circles for them. Actually, in the classroom, I would have the students who come in first. Okay, you get the idea what I've done there? I've taken my labels and I've gone back and taken up the shortcuts so well. Okay. What is the length of the little scallop down here?
By radius.
Huh? Pi times the radius. Have we talked about pi yet? Okay, he said pi times the radius. How did you get pi times the radius?
half of the circumference.
Half of the circumference, yeah? Okay. So let's back up. So the circumference is equal to what? 2 pi r. Okay, and you said it was pi r. So you said this length here, this little scale, which I'm going to cheat and just draw as a line. But you said that that line is approximately pi times the radius, which is half the circumference, right? There's a little bit of a imagine in your mind's eye. I cut those wedges smaller and smaller. That scallop would become closer and closer to a straight line, which would become half the circumference. Now, what is the? This is sort of a parallelogram, sort of, right? What is the height of my parallelogram? Radius, right? Right? What is the formula for the area of the parallelogram? Base times height. The base is, the height is, and voila. Came from someone who has qualified this. How many of you have seen this before? About half. If you haven't seen it before, it's pretty classic. One of the videos that we have referenced there is actually a video that does this virtually, electronically, and makes those smaller and smaller and smaller. It's very cool. Okay? But wait, there's more. Because I believe I have a visual proof of the area of the circle that I don't think many of you have probably seen, that I happened to uncover on the internet, and it was so cool that this has kind of been one of my motivators. So because I don't have the internet, I'm going to pretend to be the silent video. Are you ready? I'm not going to be silent yet because I'm not going to be silent to talk. But I'm going to I'm just showing you how I do this, but you can do this yourself or you can use the video, which requires something. I'm putting some double sticky tape on this paper, and you'll see why in just a moment. Because I practiced this before I got to the new one. Okay. Here we go. No sound. So what is the area of the triangle there? See that we made a triangle? You see the triangle? So what's the area of the triangle? Circumference? Height? Do you see it? Talk to your neighbor, explain what you just saw to you. So yes, okay, how do you know that the base of this triangle is the circumference of the circle? How do you know the base of the triangle is the circumference of the circle? Talk about that at your table. Okay, we're going to move on to there. How do you know the circumference of the circle is the base of the triangle? How do you know? Yeah. How do you know that the height of the triangle is the radius of the circle? In my triangle view. Go ahead and talk. See how you're questioning about discussion. How do you know the height of my triangle is the radius of the circle? And I didn't draw it. So talk about it. Okay, anyone in the room to share their thoughts about that? How do you know that the radius of the circle is the height of the triangle? Do you want to give it a shot? Yes, sir.
Basically, when you start creating the circle, you put 5 strands of beads. So the radius is 5 points. So you put all lining up one on top of each other. The height is also 5 feet. So basically, you are lining first quantity and straight line. It's going to be 5, which is going to determine the radius, and it's going to be 5. The height.
Okay. Anybody see another way? Could someone describe describe it to me in terms of the center of the circle? Yes, sir.
Well, from the center of the circle, you have 5 leads going in each direction, and so that is your radius right there. So you know that at the beginning you start with a radius of 5. When you peel all the layers, so to speak, then you end up with 5.
Sure.
So you know that that's your radius.
Mhm.
Starting with.
Anyone have another way of explaining it? Are we feeling pretty good about that one? Okay. I personally had never seen this before, and I thought this was pretty darn slick. And you don't need to have your beads from New Orleans, Mardi Gras. You can go online to www.itsthebeadone.com, and it will do the bead wrap, and it's very cool. You can show it to your students in there and play with it in class. Hope you enjoy that one. I thought that one was really cool. How many of you have seen that before?
You just started, it's called circuit proof.
You saw it before? Circle proof, yes. Now you've all seen it, right? So you got something new. I'm very excited about that. Okay, we're moving on. We're moving on to volume. Okay? So another one of my big videos is this talk or a few videos about volume. And again, if I had it in there, I would show you right now. And so I am the YouTube video here. Right? So here we go. Just for fun, I'm going to try and do the video.
I get paid $3.
He wasn't even prompted to know what to do. What does that tell you?
We have 3 radius.
Or maybe you've seen this before. What about you? Oh, you're oh. This is why you need a video. You like 4 questions.
Is that
It's LA City Water.
Yeah, we could estimate. Okay, what do you think is going to happen? Shelley's going to spill the water. That's what you're going to do.
how many of those
How many of those do you think we're going to need to fill this up? Talk to your neighbors. How many of these do you think we're going to need to fill this up?
That'd be great.
Yes. Okay, with your fingers, how many is it going to take to close right? And therefore, the volume of this is the volume of it's perfectly valid for the middle school students. Voila. If you don't want to pour water, don't go back yet. There's a video. I was inspired. But wait, there's more. I told you, it's not going to be regular water. That one I never really had too much difficulty explaining to students. It's the sphere that always used to throw me. Okay, shall we do the sphere? It's exciting, folks. Almost, because I'm sitting inside, not using
Keep you in a vision.
away. Actually, just for the fun of it, we do it differently, but I'm going to only fill it to the diameter. Just
So it's atmosphere.
atmosphere. Okay, what do right? I think it's just supposed to be.
It's some of this 4/3.
It is 1/3.
Your presentation.
Huh? It's 1/3. Okay, 1/3. So how many of these will fill up this? 1.5 of these will fill up this. We could do it. And if you don't want to make a mess, you can go online and do the video and see what we'll do for you. Okay? Or you can get your car and do it yourself. So at your tables right now, remember the diameter was the same as the diameter, the height was the same as the height. 1.5 of these fill this. What is the volume of this one? What is the volume of a cylinder? Pi r squared times h, right? And what do we know about the radius of this one? It's pi r squared, and the diameter or the height of this one. What is it? It's 2r, right? At your tables right now, see that from this information, you can come up with a formula for the volume of this. Okay. How many of these is this? Huh? 1.5. So you can figure it out. Okay. Let's take a look at some of these relationships. From the experiment, what do we know about the relationship between the volume of the cylinder and the volume of the sphere?
The volume of the cylinder is 1.5 the volume of the sphere.
The volume of the cylinder, the volume of the cylinder is 1.5 times the volume of the sphere. Do you all agree? Or, what would be another, if I reversed it, what would it be? The volume of the sphere is what? 2/3 of the volume of the cylinder. Right? Okay? I didn't pour it all because I didn't want to make a mess. But recall that I did half of the sphere and it made 1/3. So the whole sphere would be 2/3 the volume of the cylinder, correct? You can see that from the water. Okay? So let's play with this one. Okay? What is the volume of the cylinder?
Squared H.
Huh?
Pi r squared H.
Pi r squared h is the volume of the cylinder. What do we know about h?
It's the diameter.
It's 2r, right? So we have pi r squared times 2r. That's the volume of the cylinder. Yes? Okay. What is the volume of the, this is actually alternating one. Okay? All right? So this is going to be equal to, this is, wait, here we are. I asked oh, that's right. Okay. This is the volume of the cylinder. But if I want to know the volume of the sphere, okay, what do I need to do with that? Multiply it by 2/3. Multiply it by 2/3. The volume of the sphere is 2/3 the volume of the cylinder. Yeah? Okay. If I simplify this, what do I get? 4/3 pi r, which is the formula that everybody memorizes and has. Nifty, huh? Now I fumbled around a little bit with that, which wasn't very cool. But on the other hand, mentioned that I'm not the first person to come around in this class, not quite get it. And one of the things I think would be helpful would be, after we do the experiment we talk about a little bit, is to have the students then generate this formula, to have a little bit of guidance that's going to help them be productive. And so in your handout, you have a structured workspace. And I wanted you to take a look at that I provided you that you could use in the classroom. So after you've done the experiment, there are a couple ways you can go. You can do the experiment and play with it in kind of an open way like you did. Or you can do the experiment and then have the students work in a more structured workspace environment to make sense of what they saw. And if you take a look at the page which is called the volume of the sphere, it's in the middle of your packet. This is a little bit of structured workspace that would be a really nice follow-up to the experiment. The students would then start to make these connections. The height of the cylinder is the diameter, compare that to the diameter, and recognize that they are the same, recognize the diameter of the cylinder is the same as the diameter of the sphere. They would make an estimate of the heat volume of the sphere as compared to the cylinder, do the experiment, and then they've been given some structured workspace to go around we don't get that from them. You also have structured workspace for the volume of the common air in your packet. I gave that to you as well. There's also a page in there about the volume of the sphere we didn't talk about. I'm sorry, the cylinder, which we didn't talk about. That would be a follow-up in 7th grade to the work that's done in 6th grade with the volume of prisms where they're actually stacking cubes. And then it gets extended into the sphere. So there's a nice progression in the Common Core standards for the development of these. I'm going to just play with a few of them much that would be particularly interesting here. Okay. Again, these are all the experiments I did on videos, so that you don't actually need to gather all the materials that I did today. With all the structured workspace, you're welcome to use it in your classroom, and the students will be able to make sense of these formulas. They won't be so mysterious. We are going to wrap up today with the Pythagorean Theorem. It's another area of one of my favorites. And if you want to play along, there are some squares on your table. There are also some squares of paper on your table. You're welcome to play along, or you can just watch. I am told there are more than 400 proofs of the Pythagorean Theorem. And this is one that I think is really elegant and accessible to middle school students. So if you are at, if you want to play along at your table, what you will do is find a partner and have one of you take a yellow square and the other one take a green square. And you'll both take a strip of paper. In the classroom, we would actually create these ourselves. We're going to mark off a piece of the strip of paper as a ruler, yes, with a length of B and a length of A. And for purposes of making this clear, I would encourage you to make those distinctly different lengths. Don't put your B kind of midway between since the pattern isn't quite as evident. Once you've marked your B and your A, partner with green paper is going to mark the edges of the paper, the green square, as you see here. And a partner is going to mark it this way. It's also helpful when the students are doing this. I love having students do it with partners. The other, it's very useful to mark the sides really clearly in a lot of different places that we're about to have in mind. I'll give you a moment to cut that to
Yeah, but you're making it conflict.
Do you need more time?
Yeah.
Okay. Curious, how many of you have done this before? We're mathematic here. Huh? We all have. Okay, in the classroom, we will pass out scissors. Here, I'm going to trust you in a moment to do some grammatical with tearing. Okay, before we cut the tear, let's mark a few things. What is the area of this rectangle right here? We could have a conversation about is this in fact a rectangle to begin with. We'll move on. It is. What about the area of this one? What about this one? CA? What about this one? Everybody okay with that? Yes. Okay. What is the area of this triangle here? What about this one? What this one? What about this one? Now, I did not mark it yet, but this is length A, this is length B. I'm going to call the hypotenuse here C. Because the hypotenuse, because this is a square, this is a right triangle. This is A and B, this is C, they are all going to be C. Okay? Talk to your neighbor for just a moment, it's not entirely obvious. How do I know that this shape here is a square as opposed to just a rhombus? Talk to your neighbor and see if you can figure out how you would make that justification. I'm asserting what I'm asking. How do I know? Okay, so I'm hearing, I heard from one group that most is square because all the sides are equal. I did assert that this is square. Is that sufficient to know that all the sides are equal? What would the shape be called if all the sides are equal? A rhombus. Okay? But I am asserting that it is actually a square. That is, I am asserting that those angles are 90 degrees. And with one big shot, how do we know? How do we know? Okay, I'll begin. Those three angles, do you see those three angles? Have to equal what? Okay. If it is true that my right angle is a right angle, what do those angles that I just marked have to measure? How do you know that those two measures that I just marked equal 90 degrees?
Because the opposite angles are complementary. You have right and this opposite angle is complementary.
Okay. Someone want to state it another way? I want to know that those two angles that I marked are 90 degrees. Yes, sir, back. Just back.
It has to be 6 squares. You know what? 6 squares have 90 squares. So the other two, the other two angles, that's 90. The total degree is 180. So those angles have to be 90.
Beautiful. Can anybody state it another way? I know the folks in the back probably recognize it. Somebody up here in the front can state it in the front. How do we know that the two angles that I marked sum to 90 degrees? Yes.
So I know that the shorter acute angle matches the shorter acute angle, and the other angles are complementary to each other, and the 90 has to be low.
Okay. Are you all convinced that that is actually a square? It's not. It wasn't obvious it was a square. All right. So, what is the area of the square on the inside then? C squared. Okay. If you had scissors or if you want to tear, what we're going to do. Oh, we're going to cut it apart. Okay, you all agree that the yellow square and the blue square have the same area to begin with, right? This is not Penn and Keller. I'm not going to do that. You all agree, right? Oh, sure. Okay. So all of my yellow pieces collectively must have all the same areas, all of my green pieces, right? You agree? Yep. Okay. Now we're going to do a little more. What's the area of those two triangles together? AB. Oh, I happen to have an AB on this side. What about this one? Either one of those two. Okay, if the area of the yellow is equal to the area of the green, can I take equal measures away? Yes. Can I take equal measures away? And what am I left with? What am I left with? C squared equals A squared B squared. Recall that we began with a triangle that was a right triangle, ABC. And that is an algebraic proof. And now it's in your handout. So, how many of you have seen that one before?
I've seen it, but never done it.
Again, in your packet, we have some structured workspace that will be a nice follow-up to this experiment class. The students are going to take you to this experiment that they've done and making sense of it symbolically and dividing themselves. I want to thank all for your attendance. I hope that you all complete this evaluation because it is helpful to us. I'll put that back up again. And if you would like a copy of my handout for use in your classroom electronically, please be sure to either fill out an info cards or do a QR code. If you are more interested in any of the materials that you saw here, I'm actually being visited at
What you said?
427. Please come around and visit at MathLinks. Thank you all very much for coming down.